We are now at question 11, our last question of this CXC CSEC January 2014 General Paper 2 exam video solution. And part A of this question 11 gives us this matrix T equals 2, negative 1, 1, 3. And the first part wants us to calculate the inverse matrix T to the minus 1. That is the inverse of this matrix. And the inverse of the matrix T is given as 1 divided by the determinant of the matrix T multiplied by the adjoint of the matrix T. And we therefore need to calculate the determinant of T, and we need to set up the adjoint matrix of T, which is represented as this. And this is it. The determinant of T is equal to 2 times 3 minus 1 times minus 1. That is the product of the leading diagonal here minus the product of the trailing diagonal. This diagonal is called the leading diagonal or the main diagonal, and this diagonal is called the trailing or following diagonal. And so the determinant of T is equal to the product of the elements of the leading diagonal minus the product of the elements of the trailing diagonal. And the elements on the leading diagonal are 2 and 3, that's it, 2 and 3. And the elements on the following diagonal are 1 and negative 1, 1 and negative 1. And the adjoint matrix now is formed by interchanging the elements on the leading diagonal, that's it, interchanging these two elements and changing the sign of the elements on the trailing diagonal. And so to form the adjoint matrix, we interchange the 2 and 3 across here, and that becomes 3 and 2 across here. Then we change the sign of this element to 1, and then change the sign of this element to negative 1. And this therefore is the adjoint matrix. Now here the determinant will be equal to 2 times 3 is 6, and the negative 1 multiplied by negative 1 is positive 1. And so the determinant of T will work out to 6 plus 1, which is 7. And we can therefore show that. And therefore this expression reduces to this. And so it is 1 divided by 7, where 7 now is the determinant of T, and the adjoint matrix of T is 3, 1 minus 1, 2. And to finalize this calculation, we divide each of the elements here by 7. So let's show that. And this is it. T to the minus 1 becomes equal to 3 divided by 7, which is this, 1 divided by 7, which is this, negative 1 divided by 7, which is this, and 2 divided by 7, which is this. And so this is the matrix T to the minus 1, the inverse of the matrix T. Let's move down now to part 2. Now part 2 tells us that the matrix T maps the point AB onto the point 4, 9. And we are required here to find the value of A and the value of B. Those are the values in the coordinates of this point. And this information can be represented on a diagram like this. That is, the point AB is mapped onto the point 4, 9 by the matrix T. And this calculation is done by multiplying the matrix T by the column vector of the point AB, and when we do that, the result will be the column vector of the point 4, 9. And let's show that calculation. And this is it. When we multiply the matrix T by the column vector of the point AB, the result is a column vector of the point 4, 9. And we want to find AB, and so we need to transpose to make this vector the subject. Now by simple matrices transposition, the matrix AB here will be equal to the inverse of the matrix T multiplied by the matrix 4, 9. That is by basic matrices transposition of this equation. And theoretically, what really happens is that both sides of this matrices equation is multiplied by T to the minus 1. And so on this side of the equation, we would have T to the minus 1 multiplied by T. But the product of T to the minus 1 and T is equal to the identity matrix I, which is equal to 1, 0, 0, 1. And then the identity matrix multiplied by this matrix AB would be equal to the matrix AB, because the identity matrix multiplied by any matrix will be equal to that matrix. And so to calculate the value of A and B, we need to carry out this multiplication. T to the minus 1 multiplied by the matrix 4, 9. So let's go down and show that calculation. So what we have is that the matrix AB here will be equal to the inverse matrix of T multiplied by the matrix 4, 9. And we have the inverse matrix of T, T to the minus 1, as this, which worked out to be this. Now to do this calculation, we're going to use this for T to the minus 1. Because when we work with this form, the fractions here can complicate the calculations. And so we leave the fraction outside for last and carry out the multiplication with the integer values here. So let's show that. And this is it. Our column matrix AB is equal to T to the minus 1 multiplied by 4, 9. And as I said, we are using the T to the minus 1, which has the fraction on the outside. And so we'll carry out the multiplication of these two matrices first and then divide the final result by 7. And let's show that calculation. Now this is it. These codes are placed here to show the row and the column of these two matrices that must be multiplied to get the value here. When we multiply this 2 by 2 matrix by this 2 by 1 matrix, the result is going to be a 2 by 1 matrix. And this element will be the first element in this 2 by 1 matrix. And this will be our second element. And as I said, the code here is used to show the row and the column that must be multiplied to arrive at this column matrix. And when we multiply matrices, we multiply the rows of the first matrix by the column of the second matrix. And so this element here is in the first row and this first column. And so we multiply this first row by this first column. And when we multiply a row by a column, we multiply the first element in the row by the first element in the column and the second element in the row by the second element in the column. So let's show that calculation. And this is it. The 3 is multiplied by 4, and this is it. 3 is multiplied by 4, and we add the 1 multiplied by the 9. So we add 1 multiplied by 9. And when we do this calculation, the result is 21, because 12 plus 9 is 21. And then this element here now is in the second row and the first column. And so to get this element, we have to multiply this second row by this first column. This matrix only has one column, and so we call it the first column. And we are multiplying the first element here with the first element here and the second element in the row here by the second element in the column here. And when we do that calculation, this is it. The negative 1 is multiplied by 4, and that's it here, plus the 2 is multiplied by 9. And this is it. The 2 is multiplied by 9. And when we do this calculation, the result is 14, because negative 1 times 4 is negative 4 and 2 times 9 is 18. So this works out to negative 4 plus 18, which becomes 14. And then each of these elements can be divided by 7. And when we divide 21 by 7, the result is 3. And when we divide 14 by 7, the result is 2. And therefore, this matrix AB is equal to this matrix 3, 2. And therefore, A is equal to 3 and B is equal to 2. And we can show our solution line, and this is it. Our solution is A equals 3 and B equals 2. And that's the answer for that part. Let's move down now to part B. Now in part B, we are told of a triangle OMN which has the position vector of M being equal to small m here and the position vector of N being equal to small n here. OM here is the position vector of the point M on this triangle, and ON is the position vector of the point N on the triangle. We are also told that the point L is on the line MN such that ML to LN is 2 to 1. Now the first part wants us to sketch a diagram showing the points OM and L on a triangle OMN. So let's start by drawing a triangle OMN, and we can actually draw any triangle OMN. And so I am using this triangle OMN. And we're told that the vector OM is M, and we can show that vector on this line here, and that is it. The vector OM is equal to M here, and we're also told that the vector ON is equal to N, and so we can show that on this line. The vector ON is equal to N, and so that's what we have. Now we need to show the position of the point L, and as I said, we're told that L is on the line MN. L is on this line and is such that ML to LN is 2 to 1. Therefore, L divides the line MN in the ratio 2 to 1. And to correctly show the position of L, what we can do is show the ratio on the line first. And so the line will be divided such that the ratio is 2 parts to 1 part. And then the 2 parts up here really has 2 equal parts in it. And so we can divide this 2 part up here into 2 single parts. That's it. And so really L is positioned such that the line is divided into 3 equal parts. And so we can divide this line into 3 equal parts, and we do that by placing 2 dots on the line here. And now we have MN divided into 3 equal parts. And since ML is to have 2 parts, it means that from M to L we must have 2 equal parts. And so this is 1 part, 2 parts, and so this would be the point L. So let's show that, and that is it. L divides the line MN in the ratio 2 parts to 1. ML has 2 parts, LN has 1 part. And so that's the point L, and therefore the vector from O to L would be the vector OL. That is the position vector of L. And so this vector OL is the position vector of L. And that's our diagram. Part 2 now wants us to find the vector MN in terms of M and N. And the vector MN can be expressed in terms of its position vectors such that it is equal to ON minus OM. That is O times the last minus O times the first. In the vector MN, N is the last and M is the first. And the displacement vector MN will be equal to O times the last minus O times the first. N is the last and M is the first. And so the displacement vector MN is equal to ON minus OM. O times the last minus O times the first. And therefore, the vector MN is equal to N minus M. We could have also deduced that the vector MN is N minus M from the diagram. When I did the solution for the 2013 exam, I used an approach to solving the question which I refer to as the position vector approach. And it is a method that primarily uses position vectors to solve the questions. For this one, I'm going to use a method that is primarily dependent on the use of the diagram, and that is just to show another way that vectors questions can be solved. And so, using the diagram, we could have found the vector Mn by saying to go from M to N, we would go minus M plus N. That is, to go from M to N, we would go minus M, and the vector MO would be minus M because we are going in the opposite direction to the vector OM. And so we would go MO, which is minus M, plus ON, which is N here. And so the answer would be minus M plus N, which is the same as N minus M as we have here. In any case, this is the vector that we want. The vector Mn is N minus M. The next part wants us to find the vector Ml. And again, I am going to use a method today where we depend on the diagram to calculate our vector Ml. And if we look at the diagram, we see that Ml is 2 out of 3 parts of Mn. And therefore, Ml is equal to 2/3 of Mn. That's 2 parts out of 3 of the line Mn. And since Ml and Mn are in the same direction, it means that the vector ML is equal to 2/3 of the vector MN. And so we can show that the vector ML will be equal to 2/3 of the vector Mn. And we know the vector Mn is n minus m, and therefore the vector ML here will become 2/3 of n minus m. And we can expand this to isolate the components n and m such that the result is 2/3 n minus 2/3 m. That is 2/3 multiplied by n minus 2/3 multiplied by m. And so the vector ML is 2/3 n minus 2/3 m. And that's the answer for that part. So let's go down now to part 3. Now what we have so far is that the vector OM is equal to m, the vector ON is equal to n, the vector MN is equal to n minus m, and the vector ML is 2/3 of n minus m. OM is the position vector of m, ON is the position vector of n, Mn is a displacement vector from m to n, and also ML is a displacement vector from m to L. And now we are told that m is equal to the column vector 3, 6, and n is equal to the column vector 9, 0. And we are required now to find the position vector of L. Now the position vector of L is this vector here, OL. The position vector of a point is the displacement vector from the origin to that point. The displacement vector from the origin to a point is called the position vector of that point. And we are required here to find the position vector of L. And as I said, I'll be using the diagram in this question to do our calculation. And so if we look at the vector OL, we see that to go from O to L, we could go OM and then ML. And therefore, the vector OL would be equal to the vector OM plus the vector ML. And we can therefore write that the vector OL is equal to the vector OM plus the vector ML. And we have the vector OM as being equal to M, and we also have the vector ML being equal to this. And so we can show that the vector OL, which is a position vector of L, becomes equal to M from here plus 2/3 of n minus m from here. And to do this calculation, we can substitute 3, 6 for m here and here, and substitute 9, 0 for n here. And so let's show that. This reduces to 3, 6 plus 2/3, and n minus n becomes 9 minus 3 from here. That's 9 minus 3, and 0 minus 6. That is 0 minus 6. And when we do this calculation, that reduces to, and this therefore reduces to 3, 6 from here plus 4, negative 4. 3 plus 4 is 7, and 6 plus negative 4 is 2. That is 6 minus 4 is 2. And so our final answer is 7, 2. That is, the position vector of L, OL, is equal to the column vector 7, 2. And so that is the answer for this part of this question, and that is the end of question 11 and the end of this production. I hope you learned a lot, and I hope you will continue.
Daddy, you're recording mathematics the easy way for me?
Yes, Kai, but you have to be quiet. Remember, you have to be quiet when I'm recording this stuff, okay?
Yes, Daddy.
And I hope you'll continue to practice hard so you can pass your mathematics exams the easy way. And you can look forward to many more exam video solutions from me in the future. So until next time, you take care.